time dependent scattering theory theo- theoretical description uh, can be given using classical theory. So let's say we consider a classical description of a scattering theory, and in this classical description, so again उसी तरह से जिस तरह से we did in the time independent part, we started with the classical description and then we switched to the quantum description. So इसी तरह से we consider the classical description uh, of quantum of scattering theory rather, and then we would switch to the case जिधर हम बात करेंगे scattering theory, and in so doing we consider the scattering of slow electrons of a heavy atom, and we would see that this scattering wait so let's say we consider scattering of an electron, of a slow electron rather, slow electron uh, of of a heavy heavy atom. Yeah, heavy atom, and this is scattering of an electron is by some fixed atom. So we consider that the scattering is by some, or we could also consider the case where the target particle and the one which is being targeted दोनों move कर रहे हैं, but for now in the for the sake of simplicity we consider that the scattering of this electron is by some fixed atom. Yeah, and now the trajectory of this scattered particle can be divided into three parts. So the trajectory can be divided into three parts. पहले लेट्स से मैं इसको पिक्टोरियली डिस्क्राइब करता हूँ ताकि यू हैव द आइडिया of what we are considering. So we have some region. Let's say this is some region, and we have this, in fact, a particle, sorry, target, and we have the incoming beam of electrons, which basically scatter and go away in this manner. Yeah. And so we have the incoming beam and we have the outgoing beam of electrons. Yeah. And this incoming beam makes an asymptote. So this is some asymptote, and we call it as the in asymptote. In asymptote इसलिए कह रहे हैं because this electron at large distances away from the scattering center does not feel the potential of the scattering center. So that's why we call it as an asymptote. Similarly, we would have an out asymptote, and this is represented by out asymptote. And in a similar manner, हम out asymptote को describe कर रहे हैं, that is at large distances away from the scattering center. the scattered particle does not feel the potential of the target. So it would be nearly free, and this nearly free behavior is basically described in terms of an asymptote. So we describe them as an in asymptote and the I out asymptote. Yeah. And this is, in fact, this is the actual trajectory, that is the orbit. और क्योंकि हम बात कर रहे हैं क्लासिकल डिस्क्रिप्शन की, तो इसको मैंने कहा एक्स ऑफ टी, एंड दिस इज बेसिकली द टारगेट। ये जो है, दिस इज इन फैक्ट, दिस दिस इज इन फैक्ट टारगेट एटम, target atom. This is the approximate region. So we call it as an approximate region of interaction. Region of interaction. This is basically, this is in fact the the out trajectory. Yeah, so this is the in trajectory and this is the out trajectory. So the time here is t is tending towards minus infinity, that is at very far away from the target, and here we considered the description of the outgoing particles at time t is equals to plus infinity. So these are the three regions. So this is the first region, this is the second region, and this is the third region. So we have basically divided our scattering regions into three parts. That is, those three parts, कौन से? Number one, which is the part where the electron is approaching the target, and along this, in fact, region, basically the path is almost straight, and until it reaches the interaction region. And when we say the path is almost straight, इसका मतलब हमारा ये है कि we are saying that at large distances from the target, the particle is free, yeah, does not feel the potential of the target. So we would say approaching electron along an almost straight का मतलब, this is almost straight, that is, it is not in fact feeling the potential of the target, but it changes its path as it is, as it nears the target, until it reaches its interaction region. Yeah. So this is the first region. Number two is basically in fact, in the region where we have the interaction, and this region is some complicated orbit along the interaction, and we call it as complicated because it may happen that there is an incoming particle hits the target particle and there is no outgoing particle, meaning that the incoming particle is absorbed by the target particle, or it could happen that there is no incoming particle, and the target particle or the particle emits a particle, then there is just the outgoing particle and there is no incoming particle. Yeah. And so this is basically the case where there is an emission of the particle from the target, and there could be some cases where the incoming particle is absorbed and is excited to the other states of the target atom or the target system. Yeah, so it means that at the interaction region, the orbit is complex, or orbit has some complicated description. And for the case of, or for the sake of simplicity, we are not considering those complicated orbits at this moment. One could consider those complicated orbit, but this would amounts to the complication in the derivation of this scattering time dependent scattering theory. So for now, we would not consider the case where the target particle is placed or the interaction region because of its complexity. But still, we have to talk about few words about that region. So, in fact, the second part is possibly a complicated orbit, possibly a complicated orbit during during the interaction. This is the interaction region during the interaction, i.e., in the interaction region. That is a region where the incoming particle interacts with the target particle. And obviously, there has to be, because we are talking about the scattering theory, so there has to be some the outgoing particle. So that would be the departure of the electron along some, again, along some orbit. And that orbit, along some orbit, that is basically at the start, that is not straight, but as it moves away from the target, it becomes uh, uh, straight. Yeah. So along some other approximately straight orbit. So these are the three regions which we need to study. Then what is very important to consider here, that this interaction region is no larger than few atomic diameters. And so basically when you say that it is not a very extended region, or is not a very large region, or just in fact a region of corresponding to few atomic diameters, then it is unobservable. You will not be able to observe it in some detector, for example, in a cloud chamber or in a bubble chamber. What you would see in such an scattering process, not these three regions, but just a pair of straight tracks corresponding to free motion of those electrons, or whatever the incoming particle is made up of. That is the free motion before and after collision. So you would not be able to observe the interaction region. And why is that? Because the interaction region is just a few diameter in size. So the only thing you would be able to see is basically two straight tracks. Yeah, straight tracks. Why? Because they would be after interaction they would be free. So you would just see two straight tracks corresponding to the track before collision, and the track corresponding to after collision. So the यहाँ पर हम ये conclude कर सकते हैं कि the interaction region is no larger than few atomic diameter diameters, and so is unobservable. That is the region, and that is the interaction region is unobservable. That is in some some detection experiment. The interaction region is unobservable. The interaction region is unobservable. Yeah, so this is basically the consequence of this, that the interaction region is small. And what we see all uh, one can observe in a cloud chamber, let's say, in a cloud chamber or a bubble chamber. These are the devices, detection devices. Bubble chamber is in fact a pair of straight lines, pair of straight tracks corresponding to free motion of particles before and after collision. Yeah, so this is what is observed, and therefore, in seeking some description of scattering process, one should suppress that precise detail of the orbit in the neighborhood of the target atom, and one should just amplify or describe in detail the regions which are basically 1 and 3, that is before collision and after collision, and we would in a similar manner just we did in the time independent case, that is the scattered particle contain the information about the target, and so but now here in the time dependent case, again the scattered particle carry the information about the target, but now that information is time dependent. Yeah, so the only difference between that and here is basically we are talking about time dependency. So we would say that uh, therefore one would seek, therefore in 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 searching for or seeking a description of a scattering process one should not talk about or suppress, uh, in fact suppress that region which is in the neighborhood of the target, suppress the precise precise details of the orbit in the neighborhood of the target atom, of the target atom. So this is something which is basically due to the limited region of the interaction region, जिसकी वजह से हम ये बात करें, and the other very important reason is that there could be a very complicated orbit in the region जिसको आप interaction region कह रहे हैं, and so if the information about the target can be obtained from the scattered particle, then that is much more simpler as compared to, in fact, giving some details of the orbit near the neighborhood of in the neighborhood of the target atom. And so, what we need to do, we concentrate, and so and one then concentrate on the and we need to concentrate, or we need to compare the incoming and the outgoing beam, sort of we subtract the incoming beam from the outgoing beam, or outgoing beam from the incoming beam in some time dependent manner to obtain the information about the target. So we concentrate on the relation between between the asymptotically free incoming, between the asymptotically mm, free incoming and outgoing, incoming and outgoing trajectories. ओके सो दिस इज व्हाट वी नीड सो अब आपको ये अंडरस्टैंडिंग हो गई कि ये टाइम डिपेंडेंट जो डिस्क्रिप्शन है कैसे दिया जाएगा वी हैव थ्री रीजन्स वन इज द इनकमिंग रीजन one is the interaction region and the third one is the outgoing region the incoming region in the incoming region the particles are asymptotically free in the outgoing region the particles are asymptotically free but carry information about the target the interaction region is very small, that is, it is a few atomic diameters in extent. So one would not consider in detail the description of the interaction region, but we need the information about the interaction region, and that can be done with the help of the outgoing particle. Now, since we are doing classical description for the scattering theory, so we have a classical equation of motion which is a time dependent equation of motion, and that is known as the Newton's equation of motion. So let's write Newton's equation of motion, which is a second order differential equation in terms of the potential. That is the potential sort of seen by the incoming particle of the target atom. So now the orbit जिसको आप x of t कह रहे हैं is in fact a solution of the Newton equation is a solution of Newton's equation and Newton's equation in terms of potential. That is, the solution would be for x double dot of t. X double dot of t का मतलब that is a second order derivative of position with respect to time, and this is equals to minus gradient of the potential which is v of x. And you have to think about that हमने यहाँ पर v of x लिखा है instead of just v. Here we are trying to emphasize that the potential is localized. Yeah. So this is basically ये जो है this is localized potential. And why we are saying this is localized potential? Because we want to sort of suffice our if our understanding that at large distances away from the central potential, the particles are free. So if the potential was not localized, then the particles would not be free. That is our assumption that the particles are free at large distances away from the central location would not be true. Yeah. So in order to make our assumption valid, we need to think about that this potential is localized. That is localized at some position. So this is basically a generic scattering experiment. That is the particle at infinity far from the scattering center. That is at time t is equals to minus infinity, and the particle is on a trajectory which is x of t. Is not the same as and is in asymptote since it is a free trajectory, but it tends to be free trajectory at infinitely far away from the scattering potential. So although the trajectory is not in fact a free trajectory, but since it is uh, or comparing the sizes involved or the distances involved, we could approximate that the trajectory of the incoming particle is almost free at very large distances. So in some typical experiment this could be the case. And uh, uh, we could also think of that in fact along the trajectory that is x of t in some fixed time it interacts with the potential, and it remains there for a finite amount of time, and then in that brief moment of time it captures all the information about the target, and then it flies away from the target and goes out as the outgoing beam. So this is basically some description of a some generic scattering experiment जो कि हम लिखेंगे तरह से होंगे. So we just say that this is some sort of a generic experiment, scattering experiment, where we have a particle coming from very far away at t is equals to minus infinity along some trajectory which is considered or which is assumed as free, although it is not free, but since the distances involved and the sizes involved are very distances are large and as compared to the size of interaction, plus the potential is localized, so the trajectory is asymptotically free at large distances in past. Yeah, so we would say that this is some this is some generic scattering experiment. Experiment, i.e., the the particle at infinitely far in the past